Welcome everyone. I'm Michal Georgiou. I'm an architect associate professor at the Department of Architecture of the University of Nicosia. Most of you already know me. I've been torturing you for 2 weeks. Yeah. So this is the end of our 2-week workshop. I'm going to do a very brief introduction. And then we're going to move right away to the presentations from the students. And then finally, we're going to have a keynote lecture to conclude the evening for tonight. And then there's going to be like a networking event at the lobby at the entrance of the school. So our workshop for this year under the Masters in Computational Design and Digital Fabrication in collaboration with the University of Innsbruck is titled ChessMake. Technically, this is under the fabrication module 570. Okay, so the full title is ChessMake Reverse Engineering Industry Waste Analysis, and based on the work carried out in previous workshops, we are trying to reuse scrap material, leftover material, combine it with digital fabrication to produce real scale, if you like, or large scale prototypes. The tutors for this workshop, is Panos, the University of helping us, the students. We have material sponsor physics science. We've used leftover material and software support from Dot Product. The workshop ran from the 28th of November until today. That's the final day, and it was the first actually blended workshop. Our first ever workshop was physical. The second one was purely online, and this one is the first one that we've actually combined physical and online presence. Now, as I have already said, we've used scrap acrylic leftover pieces that would end up probably landfills. The equipment we had accounted for in our brief for this year was our own brand new laser cutting machine situated downstairs at the fabrication lab, and a manual bending machine, resembling obviously the process we could have been carried out with the CNC bending machine. Also, we've used LiDAR technology to register the leftover pieces. So that was mainly the equipment we've been dealing with during this workshop. So for those of you that are not familiar with LiDAR, so it's a new, very promising, very new, but a very promising technology, especially for 3D scanning, right, and registering 3-dimensional objects. Many of you are probably having it on your phone already without knowing. So we mounted one of these cameras to the laptop computer. We laid the leftover material flat in the space we are actually sitting now. We 3D scanned them. We wrote some custom-made scripts, computational scripts, to automatically register the boundaries, the 2D boundaries, where the students nested, either laid out the parts that were supposed to be cut. We had one last part, how we would position these pieces on the laser cutting machine. We went with a low-tech solution. Basically, we printed these pieces, right? So we knew exactly how they are positioned on the laser cutting machine, so we can cut them. The process was quite successful, right? So we managed to approximate exactly the leftover pieces and cut out the parts from which these pieces are made. Now, our approach, basically the design brief, encountered a highly constrained bottom-up approach. We started design explorations that should be initiated from addressing issues such as logistics, fabrication methods, stability, jointing techniques, right? And we aim for proposals that would offer realistic solutions to the above problems before proceeding to larger, right, larger assembly. So we started from smaller systems right before producing the actual. You can see some component right approaches here from the various scripts that we're going to explain very soon in detail to you. Now, the workshop was also framed from a series of other events over these 2 weeks. So we have quite a lot of site visits, both in buildings that exhibit complexity, right? And and computational tools and methods have been applied for their construction. Right? We visited industrial digital fabrication machinery sites, right? So we've seen projects produced with this machinery. We had a lot of events, both online and physical, like the one we have today, here and in other venues. We had discussions and talks. We had some social gatherings, despite being very careful, right? And we've fully documented every step, right? Hopefully, we're gonna have a short film documenting the entire process, hopefully with a new video. So that has covered what we've been doing over the last 2 weeks. So now I would like to invite the first team of students to present their work. I guess Mana and Christopher, yeah.
Sure. Hello, everyone. This is Team Christopher and Mana. I'm Mana. I flew from the United States, but I'm originally from Japan. Okay, so we're going to present our chess piece design and process. So our project kind of started with this origami inspiration. We were playing around with how it can join and form 3D. And this is showing how 3 pieces of same shaped component can come together.
Yes, these were mainly our next process after the origami papers, but maybe a bit of thicker material, the cardboard, and to see how they join together. And yes. Yes, and then also we want to play with the colors a bit more and with the pattern, how it will look with the flat surface and also with not chest-shaped objects. And some more iterations of different shapes, changing the polygon amount or triangle amount.
Yeah, so the first mock-up that I created with the origami, it has some overlaps. So as you can see in this mock-up, we quite simplified the shapes, so there's not too much overlap, because when we consider thickness and try to assemble it, we're gonna face challenges. So in this mock-up, we saw that we can simplify some pieces, especially the triangles and how it comes together. Based on that 3D printed overall shape, we try to create components that are simpler but also easier to fabricate. One challenge that we had was we look at those pieces and then join them together with cable ties on the end. And then we noticed that as you can see, it collapsed because we don't have anything to stabilize this part. So in this example, you can see that there's nothing that's supporting the middle part that's connecting and stabilizing the components. So we decided to create something in the middle to join all the pieces.
Yes, so first, so I think from maybe day 1 already, I I started to work on a script for everything. And because we did so many iterations, it really helped us with the different kind of tiles and different kind of shapes. I think it really helped a lot. And here is the overall shape that's behind this piece. It's a tapered cone shape, which is then been relaxed, or the mesh is relaxed. The anchors at the top and bottom circle. And then the next piece of the script takes the overall shape and triangulates its surface and creates little holes with the center points. So some of the holes are larger and some smaller. As you can see, depending on where the panels are. And then all of these panels are then unrolled from this 3D model and being nested already kind of nested, then will be ready for laser cutting. And it's also hard to see, but there are also holes here that are marked, and also here you see it's 2, so it's also numbered ready, so we know where piece looks.
So we decided to go with this triangle minus triangle shape, and then we had 67 pieces that are created by 201 joints. First, our challenge was to make it simple for fabrication, because when we first calculated, we had to use 900 cable ties, and that's a lot of cable tying. So we did some iterations. So on the left, we have zip ties, which is 2 per edge, and then we have bolt, that's 1 per edge. And also talking about the joints that I talked about earlier in the middle, we tried to put the triangle shape in the middle to stabilize the 3 pieces. And then we initially had a rectangle piece that supports the edge, but then we also tried a pyramid that could also align with the 3 panels that we put on top of. But then we noticed that 3D printing that piece, one piece takes more than 1 hour. So imagine having 67 parts. That's going to take a lot of time for fabrication. So we simplified by just creating creases to create 3D piece out of 2D panels. So this is our process of creating, transforming 2D panel to 3D. And then at the end, we have all these pieces formed into 3-dimensional piece. And thanks to the numbering done in Grasshopper, we were able to connect those edges efficiently and then just roll it on top of each other.
I don't know what's good. In this case, not so good, but one of it's 1 or 2 broke. But since we have it numbered easily, we can then check what number broke and then go back to our laser cutting file and send it to the laser cutter and have a new one in a few minutes.
So this is showing, it was this morning, we assembled everything this morning. It was challenging to get it stabilized because the bolt kept, we need to keep it loose until we have the time machine. That's the process. And then this is our final piece.
Yes, and then also further developments, so some lessons learned is we have this joint pieces you can see on the right that we were 50%, let's say, manually manufactured and other 50 digitally. So we didn't have the same exactness or same tolerance as our other digitally fabricated, and that then creates some deviation. And also, what would have helped a lot is numbering of the edges also. But we did have a main number for the pieces, but numbering the edges or marking them so for easier know which edge belongs to which edge.
Yeah, and then when we were fabricating by hand, we noticed that we were putting 3 components together, 3, 3, 3, and then putting everything together. So maybe what we could do next time is have a larger piece with more components, and then take this as one component. So it's gonna be more bending instead of bolting. Bending takes less time, so it'll be a more efficient fabrication process. So that's it. Thank you for listening.
Good evening. I'm Eleni, and I'm from Athens, Greece. I'm Magda. I'm from Athens, Greece. So we're going to start with some initial shapes, like really quickly. We tried some basic geometries like these ones, but they're bending. They're bending. In the middle, so we can have the sense of depth. The difference was only that the one component is more curvy, the other one is edgy. It's more edgy. And the connections we were thinking to be like slots. So this kind of shape, surface. Then we have this. This was the first, like, we were trying to find a solution. So we had this shape. We're trying to load it like that. Trying to understand how many components, how many pieces of this we have, if we have a grid 4 to 4, 4 to 3, so to understand the shape how it would be, but the fabrication time, what will be. And here it is, if we can have like a lot of them, we will have this shape. And the other is, this one with 3D printing also, is this one. So we're trying now to make these joints because the slot wasn't very good. So they did this something to be more stable. So we find this joint to be very stable, but we didn't have the bend. So after that, we went to this solution. So no, I can't. So the final component is consisting by this basic geometry that is rotating 90 degrees, and they're crossing each other. And the next part is flipped. So here we have like 2 directions. We have this one, we have this direction that it's bended in the middle, and then we have this direction that they're waving this horizontal direction. So we make this waving pattern, and the next step is to find how the horizontal axis have to bend 60 degrees. Like, for example, this is a circle. So bend it manually 60 degrees. So we will make the rings. And then for the horizontal direction, we just have like a light bend and make the weaving, sorry. And also because we wanted to add some depth from the leftovers of the holes, we've added between the two layers, like 2 or 3 of them. So we tested the joints. So we did like a small example, but
So we had one here, and had the weaving, and here we have the bedding.
There is the pieces from the holes. It's like
Different surfaces, how we do see the same.
so we've used Rhino and SQL Grasshopper to populate our component. So I think that when we unroll the whole shape, our components were like strips. So, but like the vertical strips that they become a circle, and then we have the horizontal and the vertical strips that they did the weaving. So in the middle, we have bolted these 2 layers, and then we started to weaving, but we saw that it's difficult, and the material finally doesn't have this this rate of bend, if I'm saying right, sorry. And we had some, we broke some, then we had to heat some parts with a heat gun, so we can have like our final result.
Yes.
Okay.
We used the bending, we bent 60 degrees to these ones, and this one because it was like a small apple. We didn't know what to do. First we did like that. We see that it will grow. So we with the heat gun, we gave a little angle, so we not broke the rest of them. Hello, I'm Becky Comportea. This model is more like a research model.
Can you try to speak a bit louder?
We started with this component initially. It's like a polygon with a hole. We use this the material that we cut, and we use it for making a log. This model has the advantage that we using this material, but it was not interesting. The design and the joint was very, very stiff, and we couldn't. It was strong but very stiff.
Next, we like another design of the block. That's basically our concepts in the block. So we developed a shape that could be inserted and then rotated to lock itself in the place and doesn't move. But this was actually a bad idea because eventually we found that the whole component cannot be bent and it just stays in the place like the next sketching. Yes, it had like a straight design, so it couldn't be bent or moved or anything. So
It was very solid, but not. It has no plasticity. So we cut some material here,
and we left room for the joint for the lock to move. So we thought that this would be much easier for.
It doesn't have much space to go forward and backwards.
It had more plasticity. It was strongly locking. So, but the design was not interesting.
We could get them the bending was in all places, so we couldn't like shape the bending as we want. This was the one of the component as
Then we started experimenting. We're searching for an element that would bend easily, a joint that could be strong with a minimum effort and could offer plasticity to our construction and an interesting outcome. We experimented with different totally
different design.
But the locking was not very stable, and the element was very brittle at this point that was bent.
Yeah, they were actually easy to break. So, and also the locking mechanism was not that efficient as the previous ones. So we had to move to another idea. And yeah, this one was a cutting technique that basically makes acrylic more elastic and could be shaped as the way we want. But the disadvantage of this technique is it's extremely brittle element and it could break it. The breaking point of it was like, yeah, this one like this, it could be easily bent, but at some point it could like break on this one. Yeah, it's easily break. So we had to find another technique to cut, or these are actually the lines of how we cut. Basically, the red lines are cutting lines, and the blue lines are engraving lines. And they had to pass half the thickness in order to meet from the both sides. So this was from a side, and this was from the downside.
This is 5 millimeters acrylic.
We tried straight cutting lines instead of just engravings, but as you can see, we didn't have any bending.
It has a small bending, a little bending, but not the one that we wanted. So we kept going with these elements. We designed this one. It was the most successful. It has great bending for acrylic. It was a strong element, but the element was bending only from one side, one direction. We wanted an element that would bend from the two directions, X and Y.
We tried here combining the two techniques, the engraving and the cutting, but it was worse than the engraving itself. It breaks more easily.
But it was our challenge. We wanted to make this model. It was full of curvings, and it was very difficult to achieve it with the acrylic. Then we tried to make this pattern. Making in a rhombus, so that we can fix our element. But this material in the center couldn't let the element to bend. So and then we had this.
And we made the lines thinner than before, so you could bend easily in every dimension. And here's another one.
We had achieved our goal, but it was very difficult. To assemble. We had to solve the joints issue. Eventually, we used these rings here to hold the whole structure because it was very fragile,
keep the bending and the shape of the circular section. So we had to take a section in the middle of every row and make this as a ring to hold the shape in place.
So we bent acrylic the element at the bending curvature that we wanted. It was a brittle construction though, and it was very difficult to assemble. This is more photos, they're very fresh. This is in Rhino. We used mainly Rhino and AutoCAD and grasshoppers for the mapping. The conclusion is that the design of chess piece needs more research. The bending acrylic without heating is a challenge that we could research also. This workshop taught us how difficult is the production of a design, computational design, and the publication, but also very rewarding.